This video is all about unit conversion and how we solve unit conversion problems utilizing this process called dimensional analysis. So dimensional analysis or unit conversion are just our names for the method that uses equivalence statements. So setting two things equal to each other, finding two things that are equal to each other to convert one unit of measurement to another. So equivalent statements relate one unit to another. For example, 1 inch has 2.54 centimeters, right? Every inch is about 2.5 centimeters. So what's another example of an equivalent statement? There are lots in everyday life. How about a simple one? Do you know how many inches are in a foot? If you grew up like I did using the British system, you know that 12 inches are in every 1 foot. So, I mean, it could be some some easy equivalent statement that you happen to know. We use these to generate conversion factors. So 1 inch is 2.54 centimeters, can give this equivalence factor in two different fraction forms. You can put 2.54 centimeters over 1 inch, or you can put 1 inch over 2.54 centimeters, and those are how we're going to write our equivalence factors. Okay. So a dimensional analysis problem is set up with the conversion factor arranged so that whatever the unit you've been given your number in cancels out. So you need your given unit to cancel in your numerator and in your denominator. It's really like the given unit, the given amount and its unit are just over 1 so that nothing else is there. I like to put 1 there as like a placeholder so we don't accidentally put something else. Then the unit that remains at the end is our desired unit. So if the given unit is centimeters and the desired unit is inches, which conversion factor should we use? So what we're saying here is we're given a problem that says we have blah, blah, blah centimeters, okay? And they want us to get that to inches. Okay, so again, we have blah, blah, blah centimeters. I like to put that over 1 just so that nothing else gets stuck in that denominator on accident. And we're going to multiply by our conversion factor. We're going to bring centimeters down to the basement. Do you throw things in your basement if you have one that you don't really need anymore, you aren't really using? I don't exactly have a basement anymore. My main floor is more like my lowest floor, small house. But I grew up with homes that had basements, and in our basement we would throw things before we would have a garage sale or before we would donate them. So anyway, things are getting rid of in the basement, like this unit. Centimeters can go down in the basement. And then we're going to go to inches. So we want to be in inches. We want centimeters to cancel out. So we're going to need that in every 1 inch, there are 2.54 centimeters. That's how we figure out that we need the one that's 1 inch over 2.54 centimeters to get our answer in inches. So that's the idea with picking the right equivalence factor and then setting it up correctly, which part's on the numerator, which part's on the denominator. So we need this systematic approach to dimensional analysis. We're going to write down our given amount and our unit, and then the unit we want to find. So like I did blah, blah, blah centimeters, we want to go to inches. We need an equivalent statement, so find the needed equivalent statements and set up the conversion factors. And we need to solve the math. When we're solving here, we are really, doesn't exactly fit, but I want us to write in here that what we need to do is multiply fractions. That's the math skill here, is just multiplying fractions. So I'm not fitting that in so well, but I think you get the idea. I want us to just focus on our multiplying fractions as our math skill. And then we want units to cancel. That's super important. And we want to have the right number of significant figures in the end. Okay, so let's try one together. Convert 40.8 grams to kilograms. Okay, so we're going to have 40.8 grams is going to some number of kilograms. Now we need an equivalent statement. Do we know how many grams are in a kilogram? I like to think of which one's bigger. In every 1 big kilogram, how many little grams are there? Hopefully you said 1,000. Okay, so we're going to first write down our known. So we write 40.8 grams and we put it over 1. So we don't put anything else there. That's kind of like a placeholder. Any number over 1 is still the number. times, we're going to set up our equivalents. So we are going to bring grams down to the basement because we don't need grams anymore. We're going to donate them, and we want to be in kilograms. And every 1 big kilogram has 1,000 little grams in it. So we find our answer by dividing by 1,000. So you can pause. You can use your calculator if you want. And you'll have 0.0408 kilograms. Now, when we check sig figs, I mean, what I want you to notice is that we had 1, 2, 3 sig figs going into our answer. This equivalence factor is unlimited in terms of sig figs. This one's got 3 sig figs, our 40.8. And our answer, the leading zeros don't count, and it has 1, 2, 3 sig figs as well. So we have followed our rules of sig figs and our process for dimensional analysis. Now, I should say, you may have learned some shortcuts that will work in a problem like this, especially base 10 problems. However, this process, it becomes longer and more complicated with wacky complicated numbers in chemistry. So I really beg of you to embrace the process and learn it so that you'll be able to apply it to the much harder problems. Okay, so determine, and they get harder right away, so I'm like showing you right away, but anyhow, determine the number of moles of copper in a sample that contains 4.25 times 10 to the 21st atoms. Atoms are teeny tiny, so in a reasonable sample size, we have a lot of atoms. So we use our own special unit. It's called Avogadro's number. Sometimes just NA for number Avogadro. And Avogadro's number says that 1 mole of any substance has 6.02 times 10 to the 23rd atoms. We'll get into that a lot more later, but we can use it as an equivalence factor. So, here's our number of atoms, and we're trying to get to moles. So there's our known in atoms, and we're trying to get to moles. So we're going to write down our known, 4.25 times 10 to the 21st atoms. We're going to put that over 1. We are going to bring down atoms because we're putting those in the basement. We're going to donate them soon, get rid of them. And we want to get to moles. Now we know that for every 1 mole, there are 6.02 times 10 to the 23rd atoms. Now we're just multiplying fractions here. By the way, atoms cancels out with atoms. We're multiplying fractions here. 4.25 times 10 to the 21st times 1 is still just 4.25 times 10 to the 21st. Divided by, multiplying by 1 on the bottom is not going to change this. This is 6.02 times 10 to the 23rd. Now, a couple of keys with multiplying fractions in your calculator. I'm going to even switch colors, so important. You have to put parentheses around everything in the denominator to get it all to go into the denominator. Let's say you can't remember where you put parentheses. Well, you know what? You can put parentheses around everything in the numerator and everything in the denominator. It's really not much more work, and it's a big reward. Okay. I'm going to show you my little online calculator. I've got 4.25 times. I like to go 10, and then I like to do y to the x. 10 to the 21st. So I did y to the x. And look at how it's 4.25 and then to the 21st. I'm supposed to assume that that's 10 to the 21st. Okay, then I'm going to hit divide, and I'm going to do parentheses. And look how it shows me I'm putting this denominator in parentheses. And that was 6.022 times 10 y to the x, and then 23rd. And then I'll do in parentheses, and I'll get 0.00706. Now we had 3 sig figs, so we should have 3 sig figs here. Okay, so the answer we got on our calculator was 0.070574746. You would not want to write all that down. We don't have that level of precision. Our conversion factor is considered, to have unlimited sig figs, or infinite, if you will, sig figs, so that doesn't factor in, but 4.25 has 3 sig figs. So our answer needs to have 3 sig figs, so we need to go and cut off at 1, 2, 3 sig figs, or we'll have 0.00706 6 for our final answer. Oh, and by the way, the unit there is moles. We always want to have a unit on our answer because we want our numbers to have meaning in chemistry. So it's really important that we all get the same answer. 0.00705 wouldn't be correct. 0.0070575 wouldn't be correct. We got to have the exact same answer here because we can. Because all of our rules tell us exactly what the answer should be. Okay, convert 0.041 liters to milliliters. So we're going to do liters to milliliters. Our conversion factor there is in every 1 big liter, how many little milliliters are there? That's right, there are 1,000 little milliliters. Okay, we're going to write down our known 0.041 liters. We're going to put it over 1. We're going to bring down liters, and we're going to get to milliliters. So in 1 big liter, there is 1,000 little milliliters. Liters cancel. And then we should end up with 41 milliliters. So really, you're just taking 0.041 times 1,000 to get 41 milliliters. Now, do we have the right number of sig figs? Let's check. At first, we had 1, 2 sig figs, and now we have 1, 2 sig figs, and we have units. All's well with the world. When we cross out units, we'll remember to put units with our answers. So really, canceling units and having the answer have a unit and having the right number of significant figures are all really important for our calculations, for our dimensional analysis and our unit conversions. All right, let's try some more. Let's try multi-step problems. These get kind of fun. Okay, this says 453 centimeters needs to get into yards. Okay, we are given the conversion that 1 meter has 1.094 yards. But we've been given centimeters, so we need to use our own meter to centimeter conversion. Which one's bigger? A meter. So 1 big meter has how many little centimeters? Yeah, 100 little centimeters. Okay, we're going to actually need both of these conversions to accomplish this one. Okay, so 453 centimeters over 1. Bring down centimeters. From centimeters, we know how to get to meters. We can't go straight to yards. What we're going to do is do centimeters to meters, meters to yards. We're going through meters, essentially. Centimeters to meters, meters to yards. Okay, we know there's 100 little centimeters in every 1 meter. We also know that 1 meter has how many yards? 1 meter has 1.094 yards. Remember I was saying that a yardstick is about equivalent to a meter stick? Yep, they're really close, right? Okay, so we are just multiplying fractions here. We multiply everything in the numerator. 453 times 1 times 1.094. So our numerator is going to be 453 times 1, I'm not going to put down, but times 1.094 I can put down. And then we're going to divide by 1 times 100 times 1. Well, that's just 100. Again, if you're not sure about parentheses, parentheses on the top aren't going to hurt. They're not really necessary here, but they're not going to hurt. So take a second to grab your calculator because that's what I'm doing. I don't think I need to show you the online one for this. So I got 4.96. Now, you might ask, how'd you know how to round right away for that problem? Well, let's check our sig figs. Okay, let's check our sig figs together. We have 1, 2, 3 sig figs. We have 1, 2, 3, 4. And 100, remember this 1 and 100, that has, infinite sig figs or unlimited sig figs. So really, we're looking at 3 sig figs versus 4 sig figs. 3 is going to win. We're multiplying and dividing, so smaller number of sig figs. So we should round to 3. So we're going to round 4.9 to 6. Because my calculator says 4.955, so we're going to round that up to 6. Again, 4.9558 Well, I want to round 5 up because it's followed by a 5 to 4.96. Okay, the next problem, 5.5 cups into liters. Okay, we have been given two equivalencies. 4 cups are in a quart and 1.057 quarts are in a liter. Okay, so let's write 5.5 cups and put it over 1. I'm going to bring down cups. I know how to get from cups to quarts. I know in every 1 quart there's 4 little cups. Okay, cups are going to cancel. Bring down quarts, put them in the basement where we get rid of stuff, and get to liters. In 1 big liter, there's 1.057 quarts. Okay, quarts cancel. Multiply across the top, 5.5 times 1 times 1 is just 5.5. I'll show that to you just in case you're like, where is she getting 5.5? And then in the denominator, we have 1 times 4 times 1.057. I'm just going to worry about the 4 times 1.057. Personally, I put that all in my calculator at once with parentheses, though. I like to do everything at once. So I do 5.5 divided by, do a parentheses, 4 times 1.057, do an in parentheses, and then I get 1.3, 1.3008551. I mean, you could just go on and on, right? But we're not gonna, we know better. We have 2 sig figs. We have infinite. So how many are we gonna have? This really like our number going into the problem determines our sig figs. And I actually probably shouldn't have included this one over here. The 1.094 is probably considered infinite too, now that I think of it. I was just kind of going on autopilot looking, thinking about a number that was not like a round number. But we're really limited by the initial measurement usually going into the equation. So 3 sig figs on our last problem, 2 sig figs on this one. Let's cut it off at 1, 2, and we'll get 1.3 liters. Okay, I think I've got too much of a mess. I can't handle it. So let's try our last one. This is a great time to pause and see if you can do this one on your own before I start it now. Did you pause and try it? I hope so. Okay, we're going to do 4,576 centimeters to kilometers. Well, let's see. What do we know about centimeters? Do we know how many are in 1 big meter? Sure do, 100. So it looks like we could go through meters, right? And then to kilometers. Because we also know 1 big kilometer has 1,000 little meters. I wish I would have used more of like a lowercase k there. I'll make it look like a lowercase k. Okay, we're going to write our known 4,576 centimeters. We're going to put it over 1. It's like a placeholder, so you don't put anything else there. Take the unit you want to get rid of and throw it in the basement. Kind of where things just go to collect dust. We're going to go from centimeters to meters because we know in every 1 big meter there's 100 little centimeters. Cancel out our centimeters. We don't want meters either, so put them in the basement too and get to kilometers because we know in every 1 big kilometer there is 1,000 little meters. 4,576 times 1 times 1 is still 4,576 over 1 times 100 times 1,000. Now, put parentheses around them if you do them all at once. So you should be able to pop that into your calculator and get 0.04576, and that is kilometers. You can double check your sig figs. 1, 2, 3, 4 starting off. These don't count. 1, 2, 3, 4. So I think we're all good here. All right, next up, we're going to try a multi-unit problem. Convert 5.4 miles per second, meters per second to miles per hour. So here we've got units on the numerator and the denominator, and they both need to be converted. So we've got a conversion for miles to kilometers, but not straight to meters. So we'll have to go through kilometers. But we also know in 1 big kilometer that there are 1,000 little meters. So we can use that. And seconds and hours. Well, most people don't necessarily know how many seconds are in an hour offhand, but in an hour, I do know how many minutes there are, and I know how many seconds are in a minute. So can we use both of those? Let's do every 1 hour has 60 minutes, and every 1 minute has 60 seconds. Most people go through those for their conversions. Okay, so let's try this. 5.4 meters per second. Now, rather than just writing out meters per second, let's write meters over second. And you could even put a 1 here like we were doing before. You're just saying that this object or person or whatever travels 5.4 meters in every 1 second. So we haven't changed it in any way. Now, ignore seconds for a little while. Let's just handle the meters like we have been. We'll bring down meters, and we know how to get from meters to kilometers. We know 1 big kilometer has 1,000 little meters in it, and the meters cancel. And then we can bring down kilometers, and we now know a conversion to miles. We know that every 1 big kilometer has 0.6214, sorry, I ran the room a little bit, 0.6214 miles in a kilometer. Okay, so kilometers cancel. Now that's great because we have miles on top the way we're supposed to, but we don't have hours on the bottom. How do we get rid of seconds on the bottom and get hours on the bottom? Well, we just do the opposite of what we have been doing. We don't bring these into the denominator or the basement. We bring seconds up and get rid of seconds that way because we do know there's 60 seconds in 1 minute. And then we're not quite done. Seconds have canceled and we don't really want minutes though. So we bring minutes up because finally we could get to hours down here. We do want hours in the denominator, and we do know in every 1 hour there's 60 minutes. So now minutes cancel. Now we've got hours in our denominator, miles in our numerator, just like we want. We just need to do the math. So multiply everything in the numerator. 5.4 times 1 times 0.6214 times 60 times 60. In the denominator, all there is 1,000. Excuse me, let's get out our calculators. Okay, I'm literally doing this. Are you? I hope you're calculating this with me because it's always good to check. I got 12.080016. Do you think I should put all of that though, honestly? Honestly, probably not, right? My 2 significant figures here determine that I should only have 2 in my answer. So my answer should be 12, and it better have these important units we worked so hard on, miles per hour. Whew, that was a fun one. Okay. A car can drive 15 kilometers using 1 liter of gasoline, 15 kilometers per liter. How many miles per gallon is 15 kilometers per liter? Okay, well, we know how many quarts are in a liter and quarts are in a gallon. So that will help us get between, gallons and liters. That sounds good. And then we know kilometers and miles. I think we can do this. Okay, so we've got 15 kilometers per every 1 liter. We are going to bring down kilometers. We know that 1 kilometer is 0.6214 miles. Okay. Now, we don't want liters, so we bring it up to get rid of it. We know that a liter has 1.057 quarts, but that's still not what we want. Because we want to get to gallons. So bring quarts up 4 quarts are in every 1 gallon. Okay, so now we have miles per gallon. Miles per gallon. Whew, great. Okay, so 15 times 0.6214 times 4, and the only thing in the denominator, 1.057, so that's pretty easy. Break out your calculator. Why don't you do it with me? You get 35.27. Oh my gosh, seriously, we're going to live with it. We're going to live with it here. Whoa, that's way too much precision, right? We only had 2 sig figs, so we can only have 2 sig figs, or about 35 miles per gallon. Sorry that we're living with that big line for now, but we're just going to go ahead and ignore it. So, okay, we have one more multi-unit problem here. The density of aluminum is 2.7 grams per centimeter cubed. What is the density in kilograms per centiliter? Okay, so we're trying to get from grams to kilograms. Well, we know in every 1 big kilogram there are 1,000 little grams, so we can use that conversion. What about centimeters cubed and centiliters? Well, it would be helpful to know that a centimeter cubed is equal to a milliliter in terms of volume. Now, we might not remember offhand a direct conversion between milli and centi. If you remember a ruler, and you remember what a centimeter looks like on a ruler, you might recall that there's 10 of these little, millimeters. There's 10 of those little millimeters in a centimeter, just like there's 10 of these little milliliters in a centiliter. So there are 10 milliliters in a centiliter. You could do that. If you didn't feel particularly confident about that, you could go through liters. So this is sort of one way. The other way you could do is you could say, okay, well, I do know that there are 1,000 little milliliters in a liter. And in 1 big liter, I also always remember 100 cents or 100 centiliters. That's going to get you there as well. This is kind of like an either or, proposition. So, you can pick the way that works for you. So let's start with our known, 2.7 grams in every 1 centimeter cubed. Okay, well, let's bring down grams and get to kilograms. We know in 1 big kilogram, there are 1,000 little grams. Okay, so grams are going to cancel. We know 1 centimeter cubed is the same as 1 milliliter. That's great. We also know that there are 10 milliliters, bring up milliliters, in every centiliter, in every 1 centiliter. Okay. So essentially, this way we've got 2.7 times 10 divided by 1,000. And that's going to give us kilograms per centiliter. So we've got 0.027, and it's supposed to be kilograms per centiliter. If you want to check, oh man, not again. If you want to check sig figs, the sig figs were 2 in the beginning, and so we have 2 in the end. So again, 0.027 kilograms per centiliter. Now, like I said, we could try this using some extra volume calculations. There would be nothing wrong with doing that. If you want to see that, I could show that as well. Otherwise, you can stop if you're like, oh, I've seen enough. So 2.7 grams per centimeter cubed. The first conversion is the same, grams to kilograms, 1 big kilogram has 1,000 little grams. That's the same. But here we'd go, centimeters cubed. We'd go a centimeter cubed is the same as a milliliter. Cancel that out. And here we'd say, okay, it's easier to go from milliliters to liters because I always remember that 1 big milliliter has 1,000, or excuse me, 1 big liter has 1,000 little milliliters. Okay, and then I always remember liters to centi, or centi, is a base unit that I can remember. 1 big base unit has 100 cents. Like 100 cents in a dollar, there's 100 centiliters in a liter. Okay, and that will get me to kilograms and centiliters. So this way would be 2.7 times 1,000 divided by 1,000 times 100. Oh boy, those thousands actually cancel. 2.7 divided by 100 is again 0.027, and it's kilograms per centiliter. And 2 sig figs, my leading zeros don't count, so I've got 2 sig figs. So 0.027 kilograms per centiliter for that last problem, and there's more than one way to do it. Now, we have looked at all sorts of dimensional analysis, simple one-step problems, two-step problems, and some pretty complicated multi-unit problems. So hopefully you feel really ready to tackle dimensional analysis.